recording. So we are now recording. So yeah, it's my honor to welcome Assistant Professor Andrew Lan from the University of Massachusetts in Amherst. Andrew has a PhD from Rice and a postdoc from Princeton, and he's worked with OpenStax, a fantastic organization providing free university level, college level textbooks. He specializes in AI and NLP for personalized learning and education, specifically learner modeling and content generation and human in the loop AI. So today he is going to be talking about a new bit of work he's been doing on generating distractors, a model called DiVERT, and he's changed since we actually advertised this. He's developed a new method, which is he wants to talk about, which is based on tutor-student dialogues. It's a dialogue knowledge tracing, which is going to, I think this, I don't know, it's a world first. So the paper's out, and he's going to be talking us through this kind of latest development. I've worked with Andrew for a number of years now, and I'm really happy to say that some of the data which my company's been able to share with Andrew has contributed to some of his work. It's been fantastic to see what he's been able to do. So with that, I will hand over to Andrew.
Cool. Yeah, thank you, Simon. So let me share a screen, and you should be able to see this, right? Let me just go to full screen mode. Does this work? Like, good?
Yep, that's
great.
Perfect.
Cool. Yeah, thank you, Simon, for inviting me, and it's a pleasure to be here. Yeah, it's as Simon said, we've been working together for a bunch of years now, and really, like I would say it's not like I'm doing anything right. It's basically what Simon is doing a lot of things right. Like we've been working trying to, as an academic researcher, we've been trying to partner with a bunch of people, and and the data that Simon shared with us, and also the EED data ever since the NeurIPS Education Challenge from 2020, it was by far the most informative and clean data that I've seen, and it's since we've been working together for a while, but today is kind of like the first time I'm giving like a long duration kind of talk. So yeah, so let's get started on that. So yeah, today I'll be talking about error representations, learning content generation, and going into a little bit of student modeling, right? So this is all work from our group at UMass Amherst. Yeah, so in terms of, so ultimately, what is our goal? Our goal is to use AI and personalize to do personalized learning at scale to ultimately try to improve student learning outcomes. So here is kind of like a simplified version of the landscape that we have here. So you have students and you have teachers observing students, and then students, in daily learning activities, they go through a lot of learning actions, and then these learning actions are usually about, dealing with some sort of learning content, or processing sort of learning content, or receiving feedback, and ultimately our goal is to try to provide the best personalized action for a particular student to maximize their learning outcome. And these days, AI is becoming a larger and larger part of it. So starting from when I was still in grad school, right, we were just basically working on learning action selection, meaning that there are basically these like 5 things that the students should do. You're just trying to figure out which one's optimal. But today, obviously, with generative AI and everything, things are changing. And in particular, these days, one difference is that now you can think of the learning actions or content as being generated, and the whole set of possible learning actions that a student can take can be unbounded. It used to be, it's not the case before. It used to be that we were just working with a bunch of discrete questions, and all you're trying to do is just to come up with the optimal pace for every single student and the ordering of which these students should be going through these learning actions. But now with the generative models, you can generate everything on the fly. And now, the search space, the possible space of learning content becomes somewhat unbounded, which is great if you're from a student's perspective. However, for an AI's perspective, you're trying to figure out the optimal path for a student. Now you see that we're now searching with a somewhat unbounded space. And this probably pretty challenging, in some sense, for an AI to figure out. So ultimately, what we need to do here in order to really fulfill the potential of generative AI, we kind of need to have a very deep understanding of, number one, how learning content really works. And number two is, more importantly, is how do they interact with students to change their knowledge state. Right. So here's basically I like to put this figure out as much as possible every time I give a talk, which is why is this important, or why is this even challenging, right? Why do we need to really understand how students interact with learning content? It's because in my personal philosophy, I would say that if we are looking at all the existing pieces of learning content out there before generative AI comes into play, it's like we have all of these discrete content pieces, right? But the problem though is that I've been working on this project with a group that studies personalized mathematics problem generation. And then there, the situation is that, you have a version of the math problem, but the math problem is usually framed around certain real life topics. However, this is not the best for every single student. It could be that you have an original version of the problem, but then depending on what the student's personal interest is, then you may have like maybe this student works much better, will learn much better on a slightly varied version of the problem. So one example in that case would be that, you have a math word problem. Let's say the underlying math calculation stays the same, but you can actually personalize the framework, the framing or the setting of this mathematical problem so that it covers a particular topic that this student is really interested in real life. For example, one student likes sports, the other person probably likes travel. So you can probably frame that a little bit, right? Which means that, what we're looking at is really a pretty sparse coverage in the entire possible set of learning content. You have all of these existing pieces of material, but you need to change it one way or another to make them optimal for every single student. And what's optimal for one student may not be optimal for each other. And this is why I think generative AI can help a lot, because they can essentially help us perform interpolation within the whole convex hull of existing pieces of learning content. And maybe in the future, maybe we may even find ways to use generative AI to help us to extrapolate out of this convex hull, try to come up with an optimal learning content that isn't even there. That may not be close to anything we have originally developed, right? But the one challenge here is that in order for us to figure out what is a good piece of learning content, we need experiments. However, the situation is that when we're trying to do these real world experiments in real time, saying deploying a piece of learning content for a student, and try to observe how the student interact with the content and observe the learning outcomes. That's a very long and tedious, that's a long, important, but it could be really, really time consuming, the process. So ideally, we want to have a rapid cycle, product development cycles or research cycles. So ideally, right, I'm just talking about the ideal case, we want to have authentic simulated student agents. Because if we can have simulated AI student agents, then there really are a huge amount of potential benefits that we can reap off. For example, that would mean that as educational researchers or product developers, we would have access to a proxy of a real student, basically 24/7. And using that, we can do if we really have this authentic student agent, then we can do so many different things. Teachers can practice on this synthetic student so that to hone their teaching strategies, or should learn what kind of problems are helpful for students and automatically how to generate them. And also just practice with the student, try to anticipate, okay, if I do this action tomorrow, what are going to be some problems that come out among these students, and anticipate their errors or even reasoning flaws or misconceptions and all of that. And there are, many of these different things that can be potential benefits. However, of course, there's a however, right? So this is great, but the problem is we don't really have that, right? So there are a lot of works recently about building synthetic student agents, but making them work in an authentic way is really difficult. And Simon and the EG team has experienced this a lot. when a lot of the real situations when you want the model to anticipate student behavior, no matter how capable they are, they're still not that good at this particular task. So in this particular talk, I'll mainly talk about two components. So I have a list of three here, but I changed one part. I swapped one part out. I'll mainly emphasize on the first and the third components. So these are just some of baby steps that we have taken in this particular direction. So the first part, I will talk about understanding errors, and then I'll go into, mention this for like 1 minute of how do we do student modeling for open-ended questions. And then at the end, there's this paper that we just submitted last week, which is about student modeling, student behavior modeling and analysis in dialogues, right? So in a kind of not very structured kind of learning activities, right? So let's jump into the first one, which is our recent, this paper will appear in a month and a half. So this is about underlying errors, because we know, these days when we play around these models, I mean, they're good at problem solving. However, even if you give like GPT 4.0, I don't know, I can't say anything about O1, but yet, but if you give 4.0, like, okay, say, here's the problem, here's the student answer, tell me what error the student made. It actually doesn't do a very good job. So which means that it's not very good at understanding what error students are making. So in this particular work, this is our goal. Right. So in particular, we're working with, of course, this is data shared with us by Edie. So this is the questions about multiple choice questions, where you see that for a multiple choice question, we have a set of components. So we start with the question stem, basically just tells the student what you're doing in this problem. And then among usually a collection of 4, or sometimes maybe more, sometimes less, a number of options, there's a correct option, which we call the key. And then the other incorrect options, which we call distractors. And sometimes there are also explanations and feedback. And usually, I'm not sure about all multiple choice questions out there, but at least for in Edie's case, all of these distractors are, in most cases, deliberately designed to capture or to represent common errors among students or misconceptions. Right. So and some of these distractors, they also have associated feedback messages, which is trying to tell the student what you have done wrong and maybe offer some sort of actionable suggestion of what you can do to get this question correct. So in this particular work, what we do is we invent this framework called DiVERT, and then here, so our main goal is to look at automated distractor generation in MCQs, try to come up with high quality multiple choice question distractors. And the novelty that we introduce here is that we'll go into this extensively, which is we explicitly represent errors behind distractors as text. And we want to figure out how do we generate those and how do we use that information to come up with good distractors. And then we, to actually do that, we develop a series of techniques to make this actually work in what we call semi-supervised setup, which I'll explain later. So yeah, a bunch of technical challenges that we have to overcome to make this actually work in practice. And then we experiment on data, on the ED data, and then I'll share with you what we observe. And also in the end, I'll share with you what we identify to be the bottleneck for good distractor generation performance, after going through all of these experiments. Right, so let's begin with the task definition. So usually what we have here is that I have a collection of the question stem, the key, and then a set of distractors and corresponding feedback messages that are optional. And you can think of all of these components as either text or math tokens or a combination of both. And then our goal here in this particular work is to perform controllable and explainable distractor generation. So what we want to do here is to say that given a particular question stem, and possibly other corresponding components like the correct solution and the explanations and all of that, I want to generate a set of possible errors. In other words, what can the student possibly do wrong in this problem? And then the second part of our task is to say that for every one of those single plausible errors, I want to generate a corresponding distractor that actually corresponds to that error. In other words, if you follow that particular error, make that mistake, or follow this particular flawed reasoning process, here is the final answer that you will get as a result to this question. Right. And however, the challenge that we're facing is that, usually for math multiple choice questions, errors are not really explicitly defined, right? Like, let's just look at any sort of math MCQ data set. You just have a question stem and you just have four distractors and like nothing else. So nobody is going to go in and tell you what these errors are, which means that when I'm trying to maximize the probability of a distractor given a question stem, we really are essentially marginalizing over all the possible latent error representations that are under this, right? Which result in this particular likelihood expression. With this likelihood expression, since we see that, well, since this error space can be kind of difficult to manage, then this direct inference on this is not really feasible. So we introduce, in this case, obviously, this is kind of quite natural for for models with latent variables. We just introduce this variational pipeline where we have a bunch of components. So I'll explain all of these components later, but just to make sure that I put the variational pipeline objective here. And then in this framework, we have three different model components, which is what we care about. We actually want after our training process, we want to be able to learn these three models. So the first one is called an error generator model. What I mean here is that, so P of E given S, so just the probability of the error given the question stem. So basically, if I have the question stem, I want a model to be able to tell me, okay, what is the list of possible and plausible errors that can be made in this problem, right? So that's the first component. And then the second component is what we call a controllable distractor generation model. In other words, the probability of a distractor given the question stem and a particular error. Say this is basically just telling the model to follow instructions. Say, and under this problem, make this particular error, get a corresponding distractor as a result of that calculation. And then the third one, which is an error identifier model. So in this case, because we're using a variational framework, we have to use an approximate distribution here. However, this one you can feel free to we can freely choose to be any form. But then we in this particular work, we choose it to be conditioning on S and D, just because this model is actually meaningful. Because the meaning here is that given the question stem and a particular distractor, I want to generate an error explanation. So you can think of this as just as maybe we can call this a sanity check model, which is to identify the error behind a question distractor pair. That is actually also kind of useful in practice in some settings, because sometimes you want to just make sure that the model understands what's going on, right? Okay, so there are some specifics. I'll explain some of these later as I move forward, but I just want to, we just need to put it clearly specify that here. So for the three components, we're using three separate LLMs, right? So in this case, we're using a base open source model. Since we have to modify the structure of them a little bit, there's no way we can use the GPT model family. So we have to use an open source LLM. And in this case, we found that the MetaMath 7B model is not too big, but at the same time works pretty well for mathematics related stuff. So we used that. And the three LLMs just corresponds to, in practice, three different sets of Laura weights. Right. So since the errors, we treat errors as text, we'll use a soft token-based differentiable learning approach. So I'll explain what that is later. And then during generation, so we use over-generate and rank approach. So in practice, think about if you really want to create a set of distractors, what we do is that we over-generate errors and distractors. And now we use a beam search to try to identify, if you want three, I'll give you the top three sets of distractors through a particular metric. And there are also small tricks that we will be explaining, right? So let's just go look at the visualized process of what's going on here. So first of all, the first part is that imagine in practice, if you have a multiple choice question, the STEM, right? What I want to do is to put it through the error generation model and give me like a textual description of what a plausible error is. And text here is just in terms of discrete text tokens, right? So imagine that here's the example problem. It's a fraction divisions problem. And one plausible error among students could be, the student is now multiplying instead of dividing, right? So let's say that's one of the errors. And now you would have the second step, which is to say that given this error that you have generated, which is hopefully a plausible one that real students can make, combine that with the original problem. And then we instruct the controllable distractor generation model to say that, okay, for this problem, follow this error, generate the incorrect answer as the result. So that would be 7 divided by 18 in this case, multiplying the two fractions instead of dividing. Right. So this is the second part for the generation pipeline. And for our variational framework during training, that's the setup is that we're not sampling from the error generation model. We're sampling from this approximate model Q, which is the error identifier model. So here, what we're doing is that we have the distractors here, 7 divided by 18, combined with the question stem. I'm going to go through this and we sample the error tokens, sample all of these different error tokens. So you can sample multiple versions of it. And then we use it to approximate the objective. However, the key challenge here is that during training, right, like when I'm sampling these discrete text tokens, usually when we do all of these trainings, we use gradient descent algorithms. However, in this case, so imagine that the objective is calculated on the final distractor 7 divided by 18 here, right? So that is conditioned on the discrete error text tokens, and then that is the output of the previous Q model. So when the text tokens are discrete because of their discrete nature, it's not really it doesn't really allow us to flow the gradients. So here, what we do is that to enable this gradient flow and and for end-to-end training, we use soft tokens to replace these discrete or hard tokens. So we do something quite simple, which is just we use the output. So because these text tokens are sampled from the output distribution of an LLM. So what we do is simply we use the logits weighted text embeddings, right? Because at each one of these time steps, we would have the logit probabilities for the probability of each token at the output. So instead of taking, the one token that I've sampled and that corresponding to embedding, I'm just going to take all the probabilities and use it as a probabilistic weighted average and to combine all of those discrete token embeddings. And by doing that, this actually smoothes the whole process out. And now you can flow gradients from one model to another. And for this smooth approximation process, we do use an annealing process to control the temperature of this approximation, so that at the beginning of training, this is a very smooth process. But then at the end, it gradually the soft tokens gradually gets very close to discrete or hard tokens. And another thing to identify, the final component in our training is that because during training, the discrete text tokens are sampled from the Q model, but when we actually needed to use it for inference in real life, when we actually want to use the model to generate errors and distractors, the error tokens are sampled from this PE given S model. So we use the KL divergence term to enforce the two models to be close to each other. Right. So they are coupled together for using that part of the objective. Right, so so that's basically the setup. And for the data that we use, so we have a total of 1,434 math MCQs. So under two topics, number sense and algebra. So we have to go and among these there are a total of 3,601 question distractors pairs that are labeled with error. So these are error labels curated from real teachers. Later I'll go into how exactly do we make use of those labels in a semi-supervised setting, quote unquote, semi-supervised setting. And these errors are things like, so using the example that I just showed, this is maybe labeled as multiply instead of divide. So that's a particular error, or some of these are specific misconceptions. We have to do some manually filtering for our case because first of all, unfortunately, we have to throw away questions with images because MetaMath does not really handle images as input. But the other thing is we also, because of our evaluation metrics, we have to throw away some of these questions that are labeled with very few tags, just for the purpose of our evaluation, right? Okay, so let's talk about the evaluation metrics, right? So evaluating the quality of a distractor can possibly be quite hard. So we use a hybrid approach in this scenario to to evaluate the quality. So for distractor generation, because a distractor is a concrete thing, so we just use a series of alignment-based metrics where the human authored ones are, we use them as ground truth. In other words, we want to see if we can recover the human written distractors. Because based on our experience with the data, most of the questions have very high quality distractors that actually do correspond to plausible errors made among students. So we think that for the data that ED has shared with us, these metrics are reasonable metrics. Of course, they're not perfect. I'll explain that. Sure, and then we use these three sub-metrics, right? So I would say let's just emphasize on the final one, which is that overall across a large number of questions, if I generate with our method, if we generate 3 distractors, and I'm looking at how many of that actually do match with the ground truth distractors, and we can just find the portion of overall generated ones that are actually matching with the ground truth ones. And obviously, these metrics are not perfect because the ground truth set sometimes can be either poor or incomplete. This doesn't always happen, but it's possible because some of these multiple choice questions, just by design, if you look at the question stem, for some of these questions, it's just very hard to come up with, the second most common error. In many of these questions, they're really just like the most common error that students would make, and then the other ones are it's going to be hard to imagine. Real students do not really make other kinds of mistakes. But on the other hand, you have other types of questions where there can literally be up to, I don't know, 5, 6, or even 10 different plausible errors that are all possible. Some students would actually make those errors, but the problem is you cannot capture all of them with the 3 observed distractors that we have. Right. So these may not be perfect, but I think they are reasonable. But the other thing is for our framework, because we do generate errors as text tokens, these are supposed to be human interpretable. So that's our claim. So we actually do a human evaluation to ask human raters to come in and rate the plausibility of these errors, or on many different aspects. So I'll go into those aspects later. And here we're also comparing DiVERT with a bunch of baselines. So these are GPT-4o based. So that's, by the time we did this work, that was the best model that we could have access to. We have in-context learning with k-nearest neighbor. So that's actually prior work from our group, not going into too much details. It's just a smart way to use GPT-4o maybe. And also we have the zero-shot version where we just ask the models to do this task without any examples or any further training. And we also use a bunch of fine-tuning based baselines. So these are more like sanity checks. So the first one is that for the distractor generation task, since I have the question text, right, I also have a bunch of distractors. Why can't I just use the model to just fine-tune an LLM on this data format? We can do that. We can also say that since we have a bunch of label data where I have the humans written error labels for this question distractor pair, I can just train the model to generate, first of all, the error description, followed by a distractor. So in other words, this is kind of like a chain of thought scenario where you give the model additional information to train on. And then the third one would be that we use the same 2-step approach as we use in DiVERT, where we first ask the model to generate the error given the question stem, and then and then using the generated error, now go in and generate the distractor given the question stem and the corresponding error. So this is basically kind of similar to DiVERT, just without the variational pipeline and all the tricks that we do. Right, so here are some results. So I would encourage us to, we tried it on 2 different settings. So the first one is, since we use an overgenerate and rank approach, we can, but there are 3 ground truth distractors. So we could just generate 3, or we can generate, say, a huge list, and then we look at, maybe we generate, in this case, we also look at if we generate 10 possible distractors and different errors and how feasible they are, right? So here we see that on k equal to 3, which is we just compare the top 3, then GPT-4o KNN is the best, but then DiVERT is getting close to that in some of these metrics. But on k equal to 10, DiVERT outperforms even GPT-4o, right? So, and with this result, the other thing I want to say is that GPT-4o, we don't know how many parameters that it has. Some people say it has 1 trillion, but our base model only has basically 7 billion parameters. And we are also want to highlight that prop at 10 is probably the most reliable metric that we have, just because when we're generating the top 10 errors, for many of these questions, they're the top 3 distractors that are actually there as the ground truth may not cover all the possible errors in there. So these evaluations with k equal to 10 would give us a sense of how robust the model is, right? Like because what we found is that in many cases we can actually generate all of these good distractors within the top these plausible errors and corresponding good distractors in the top 10. However, maybe in many cases, since the actual distractors there are only 3 of them, there may not exactly correspond to the top 3, right? But they are reflected later down within this top 10, right? And in that case, we found that DiVERT works well. And the other thing is, since O1, O1 just came out, so it will likely be better than GPT-4 on this task, although we don't have the concrete numbers yet, but we'll have them, I think within this week. Okay, so some more nuanced insights is that because previously I mentioned, there are these labeled errors on these question distractor pairs. How exactly are we using them? So we're using it in a very weird way. This is what we found out after doing a bunch of experiments, is that we don't actually use them extensively during training. We use these distractor labels to warm start the 3 LLMs that we have in a fine-tuning way. Then we do not actually use them during the DiVERT training phase. So during the DiVERT training phase, what we do is that we actually, even for a question distractor pair that has ground truth human written error labels, then we still sample from the error identifier model and use that for training. I think the intuition, and we found that actually works better compared to using the human written labels during training, because I think kind of the intuition there would be that we assume that why this works is because when we actually sample these models sample these errors from a fine-tuned model to begin with, then we're actually sampling some tiny little variations around those human written error labels, and sometimes we found that doing that makes the training process more robust, and then as a result that it works better. And this graph shows that in practice we only need DiVERT works even when we have much less labeled data. So we're comparing against we're running this ablation kind of experiment where we randomly drop what are a certain percentage of error labels, right? So we see that on the left-hand side, when no error labels are dropped, then we're a little bit better than fine-tuning. But as the number of error labels that are dropped gets higher, then using like 1/4 or 1/5 of the original labels, then DiVERT is still able to perform pretty well in this regime. So in other words, we're kind of, compared to just doing this in a simple way, then this is our method is a better fit when we have less training data. And we also found that using errors as chain of thought generally do lead to improved performance compared to just asking the model to spit out a distractor. And also we found that temperature annealing is kind of useful. You need to change like how good that softmax approximation is during training, and that helps in practice. All right, so I'll give you a qualitative example. Let's just try to see what we can do with this in practice, right? So given a multiple choice question STEM, what's the lower common multiple? So we can ask the model to spit out, okay, these are the actual outputs when we sampled from the P of E given S model. And then you can sample a bunch of these natural language descriptions about errors, and then put those descriptions together with the question statement into the controllable distractor generation model, and then you arrive at the particular distractor, right? So some of these qualitative experiments that we found is that it does, compared to GPT-4, which sometimes give you a reasonable answer, but the thing is, if you think about it, it doesn't necessarily really correspond to what errors that are plausible among real students. And that's what we can pick up from using our approach by training on the data that ED gave us. And we also obviously need to conduct a human evaluation for in this case, the error representation quality, because for errors, it's really hard to characterize what is a good error and what is a bad error, what's a plausible, right? So we have to resort to human evaluation. So we did this, and we asked these experienced human teachers to rate the quality of distractors on 5 different aspects. Right. So the 5 aspects is the error relevant to this multiple choice question? Is the error mathematically correct? In other words, is this even relevant? Right. We really don't want something that's unfeasible given this particular question. And it also has to be specific. It cannot be super duper generic that is more like the safe output that language models like to give you. Rather than being specific, it has to be pretty specific to this particular math concept and this problem scenario. And we also want them to, at the same time, we also want them to be somewhat conceptual, because we don't want them to cover specific numerical errors within this problem that only applies to this problem. We want them to be somewhat generalizable to other problems as well. And the other thing is obviously the most important criteria, which is we want the generated errors to be actually plausible among students. You cannot tell me something that's correct, but it's not feasible among real students. So, and in this case, we basically ask the human experts to rate the quality of a distractor on these 5 aspects by giving them a mixture of errors generated by humans, which is the ground truth labels, which are from the ground truth labels, and from DiVERT, and also from GPT-4o. Right. So, and we don't tell the humans which one they're from. They have to they just have to do this rating without knowing that. So what we found is that human and DiVERT, they work similarly to each other. Humans work a little bit better, but this difference is not statistically significant. But both of them are statistically significantly better than the error spit out by GPT-4o. And yeah, I mean, this is not too hard to understand. It's kind of easy to anticipate, because we are indeed, both of these methods have taken into account the insights that went into the complicated process of actually building high quality multiple choice question distractors, right? So we're essentially trying to pick up on that. And yeah, we feel like, oh, one will be better, but soon we'll know how much better it is than GPT-4o. Right. So, and through all of that, so here's kind of like, after this process, what do we learn? We basically identified, we've done some things. I think the distractor generation quality we found are much better now compared to the previous version of the work we did earlier. And I think when we did this last year. But we do find one particular spot where that's the next direction for us to work on. Because the main problem, the bottleneck, is that the faithfulness is still not very good here. I mean, there are a lot of recent work showing that if you ask large language models to follow correct instructions, they do a pretty good job. But if you ask them to follow an incorrect instruction, something that doesn't make sense, they do not tend to give you, a result that's faithful to the instruction. Here's an example. So let's say I want to calculate this one, 6/9 divided by 3. And then let's say I have the error, which is that when dividing a fraction by an integer, divide the denominator by the integer, right? So in this case, obviously, the answer should be 6 divided by, and the denominator should be 9 divided by 3, so the distractor should be 6/3 or 6 or just 2. But then after this entire training process, our trained model still makes this error, which says that if I follow this error, my distractor is 6 divided by 1. That's not good. So we found that most of the cases, through manually, like qualitatively examining a bunch of these scenarios, we found that the error generation model is pretty good, because it did learn to pick up some of the what is the plausible relevant error given a question stem. However, the second part is the problem. Right? It's not faithful. So there are some possible solutions. First of all, we can use this idea called cyclic consistency regularization, which is that if we imagine what the whole process is, right, we have in the end a generated distractor. But for this model, for the error identifier model, I also use the distractor as input. So in the end, I can enforce a cyclic consistency between these two, and now to do that training, use that as an objective to try to improve the faithfulness of my controllable distractor generation model. Right. The other thing is we can also try to see that if involving symbolic solvers or even code in the loop would help. So far, we haven't really found this to help too much, but there could be better ways to incorporate those. And ultimately, so what we really want to do is to also use another valuable source of information from ED, because they've deployed these questions over the years and they've accumulated a lot of students coming in and really answering these questions. So we do know, actually, we do have some idea about what's the underlying true goal of distractor generation, which is you want to generate questions, the distractors that can be selected or frequently selected by actual students, and these distractors correspond to common wrong answers. So in the end, we were thinking about this and we're trying to use some sort of MCTS or Monte Carlo tree search based methods to kind of see if we can leverage that. All right, so that's the first part. Maybe I'll pause for some questions. Is there any question? All right, so I guess I can just go to the next part. So next part, oh yes, there's a question here.
We've got a hand up.
Let's see.
Sumit, you should be able to unmute.
Okay, sorry. I can unmute now.
Okay.
Mm.
Got two
Can you
questions.
hear?
Yep.
Can you hear?
Yeah, sure.
Yep.
Yeah.
Yeah, so I think you barely mentioned that, but what I was wondering about this, like you have multiple choice questions, right? And then you have like
Yeah.
different answers, and there's of course cases that students choose one answer randomly because they didn't find the answer in the choices. Have you thought about including or incorporating a random component in your errors?
Yeah, that's a good question. So I would say that for now, so far in this particular work, we've basically studied, we have not really looked at student behavior yet. So we're not using any information on the student side. So we are basically just studying this from an NLP perspective, where we want to just study distractor generation, like what is the plausible error for a question, right? So and like given that particular error, what the distractor should be. But for sure, like I agree, like the next step, we would be wanting to incorporate other information, which is like which student actually selected which distractor. So in that case, once we connect student models into this, either for knowledge tracing or IR, item response theory type of models, or other more advanced methods, there will be like a guessing component. So for sure, that will for sure be relevant.
Cool, thanks.
Okay, hello. My question is that after generation of distractors, let's say that you have generated 7 to 8 distractors, and there are relevant distractors. They are not, let's say, they are relevant. So how do you decide which distractors to choose? Let's say for a given question, there are 4 options. One is the key answer and other 3 are distractors. How do you decide that these 3 distractors are the best case, which are most applicable to most students? How do you decide that?
Yeah, sure. Yeah, it's a good question. So in this particular work, since we're studying this from an NLP perspective, right? So so here what we do is that we have, first of all, we use beam search to generate like a list of top errors. And then for each possible error, we also go down and then we try to generate the corresponding distractor. And we have a way to balance the 2 beam search scores so that in the end we have a rank, and then you can select the top 3. So with this case, the ranking criteria is basically the likelihood. However, moving forward, when we actually, so this is the first step, and the second step would be that in the future, we also combine with information on which student actually selected with distractor. So in that case, it would more be like a student model-based kind of distractor selection. Yes, and we have done some work on, training a model to identify, okay, like using direct preference optimization to train a model that says, okay, like I think for this question, this distractor is going to be more popular among students than the other distractor. Use that to come up with an objective function. We can also use that to rank. Yeah.
Okay, thank you.
Sure. Right. Okay, yeah, so I'll move on to the next part. So actually I changed my mind. So I was about to talk about, open-ended knowledge tracing. So this is kind of, but I figured that maybe I won't talk about it too much here. That was on more of the case that we used was for computer science education. So it's like open-ended coding tasks. But I'll actually jump to the final part, the third component, which we just submitted last week. So I think this is what I'm excited about, which is some completely new thing we haven't really tried before. So in this case, we want to look at student modeling in tutor-student conversations, in dialogues, because these things, talking to a chatbot is becoming more and more prevalent these days, and we want to see that if we can do student modeling in this scenario, right? So because prior work has shown that tutoring, especially in the form of one-on-one dialogues, is highly effective. It is shown to be lead to improved student learning outcomes. And there are plenty, and these days it's also getting more common because there are a lot of LLM-powered tutor bots such as Kamigo or Carnegie Learning's Life Hint, all of those things. And I know ED has that as well, right? So, but maybe between a real human tutor and a student. And the power of AI, the LLM-powered tutor bots have promised to be able to chat with like a lot of students 24/7 at the same time. Maybe it's good enough for scaling up human effort. And what the other nice thing about dialogues is that you can use them as formative or stealth assessments. You can think about those when the student is interacting with the tutor, because it used to be that assessments can only be done when we have students going through this particular assessment question and coming up with the answer to that question, and you can use that to assess student knowledge. But we're now looking into kind of unstructured or at least less structured learning activities. For example, just a dialogue, right? And then so basically we want to be able to look at, okay, what is the student actually saying? And does that give us any information about, their knowledge state? Can I use this as formative assessment to provide feedback or to provide useful information to tutors? And existing work on analyzing dialogues almost exclusively focused on tutor dialogue terms, because there are a lot of works trying to align large language models with pedagogical principles to try to make them behave like tutors, right? And also according to certain well-established effective tutoring strategy. And possibly, I would say one possible reason, of course, doing so is important, but one possible reason is because student discourse is actually very noisy and much harder to analyze than teacher discourse, because student discourse, they come from students who may not even talk on topic, or maybe they have very flawed or weak knowledge. They don't have a good reasoning process, right? So they may be harder to analyze. So what we do here is our experiments, or this framework, is developed on a data set shared by Khan Academy this is a very small data set with only 188 dialogues, but that were originally used for this task of math tutoring accuracy determination. So the data set was collected when Khan Academy, the initial goal was to try to investigate whether the language model is doing something correctly to respond to the student, or is this student response mathematically correct, something like that. Right? And this happens between, this data set contains dialogues between an AI tutor, which is Kamigo, and a real student. And we also use another data set called MathDial, which is larger, but then the situation is a little bit weird because that's actually flipped, because in that dialogue, they use an AI simulated student, but we know that this is not very authentic if you just look at what actually happens in that data set. But the tutors are actually humans, right? So it's kind of like the reverse situation compared to Khan Academy's data set. Right, and in the end, we have to do some filtering. I'll explain that later. But ultimately, for the main data set we're using, it's a very small one. It only has 153 total dialogues. Right, and here for the knowledge tracing task, dialogue knowledge tracing task, we basically want to do the following. So, given the entire dialogue or the conversation history in the dialogue, what we want to do is to, number one, use the dialogue history to estimate the student's knowledge levels, on mastery levels, on a bunch of things what we call knowledge components. And then we also want to use this information to then in turn predict whether they're going to respond correctly or say something correctly in a future dialogue turns. Right, so here's the visualization of our setup. So what we do is we use two sort of sets of large language models to do this. First of all, given just the dialogue without any sort of annotation, we prompt GPT-4o to first of all take the set of Common Core standards, which we take as the pool of knowledge components. And then for each relevant tutor-student dialogue term pair, we want to be able to identify, ask the model to tag what is a relevant knowledge component here. Of course, we also filter out dialogue turns that are about small talk or anything else that are not really related to, that are not knowledge related. Right? So we filter those out. And we also prompt the model to evaluate whether the student responded to this question correctly or incorrectly. Right? So he also correctness labels. So later we have a human evaluation showing that these labels are kind of, that are pretty accurate. GPT-4o does a decent job here. Right? And then using these labels, the knowledge component label and the response correctness label, we build a model which we called large language model-based knowledge tracing, LLM-KT, where we fine-tune basically the backbone is a Llama 3 model. And then what it does is that it, first of all, estimates student knowledge on all the relevant cases that have appeared in so far in this conversation, and also predict how well the student masters a particular knowledge component. And also, as a result, how likely are they going to respond correctly to what a tutor would ask them to do? Right, so here, first of all, some results on the labeling task. So we asked GPT-4o to basically select from Common Core standards. So we have to do some filtering since Common Core doesn't cover calculus, but in the Khan Academy data set, there are some calculus dialogues, so we throw them out. And then these labels. So, and we also ran a human evaluation on a subset of 20 dialogues to where we found that LLM labeling is pretty accurate. It has pretty high accuracy, and the accuracy is very similar, especially on correctness. The accuracy is pretty similar to Khan Academy's original findings. And we also found that humans do generally agree that the knowledge components identified by GPT-4o for each dialogue turn to be somewhat accurate. Although in this case, the inter-rater agreement is not super high, but mostly it's just because the data is very balanced. Like by far most of the scores that they have provided, the labels from these humans, from our human evaluators just says that the model output is basically correct, right? So that results in these low coefficients, but still, the quality is pretty good in practice. Yeah, there are some occasional errors. I'm not going to go into the details, but what this process does, this annotation process does, is that now it turns these dialogues into a typical knowledge tracing data format where you're just looking at a timeline. And then at each time step, the student goes through a particular problem about certain knowledge components, and you observe whether the student did this correctly or incorrectly. So that's a typical knowledge tracing data format. And we can now just slap on any sort of knowledge tracing method, or in this case, we actually developed something called our own knowledge tracing method. So here's what we do. We say that because most of our dialogues, our dialogue turns, actually turns out that they have multiple knowledge components. So by far, most of our turn pairs have at least 2 knowledge components. So this isn't really addressed in existing knowledge tracing work, where you usually have very few questions that are about multiple knowledge components. And there's not a lot of good baselines on this. So what we do is we use some sort of an end model where we say that the probability of a correct response at a turn is the product of the probability that the student masters all of the required knowledge component in this particular turn. So we use a simple and type of model. And in order to get that probability for the student mastering that particular knowledge component, we use this trick for Llama 3. So what we do is that we give the model an entire dialogue history up to this particular point, which tells the model what the student has done before. So what's the history? And then we tell the model, okay, here is a particular tagged knowledge component identified to be relevant to the next dialogue term. And we also asked the model, say, do you now think the student would master? Do you think the student would master this particular knowledge component at this term? True or false? And then what we do is that we just look at the output probabilities for Llama 3, and we look at only 2 tokens, true and false, and we normalize them this way. And then that would be the probability for the student mastering that knowledge component. And then what we do is that since previously using this annotation process, I have all the KT dialog data format, I would now use that information to fine-tune Llama 3 so that it now becomes a knowledge tracing model. And here are some results. So what we found is quite interesting. So on both, we did experiments on both of these dialogues. So one data set has no pre-identified split, so we can do a cross-validation. The other one has a pre-identified train test split, so we cannot. But these are, but basically these are but essentially the same set of experiments and same metrics. So what we found is that on this data, on the Khan Academy authentic data set, because it's small, on average, every dialogue has between 3 and 5 turns, just because in practice that they are kind of truncating this early just for the purpose of model evaluation when they release this data set. And there are only also a total of 150 dialogues. And what we found is that all existing knowledge tracing methods for existing purposes, they almost completely fail. So F1 scores these, all of these metric numbers, they are around 50%, which is just, you basically learn nothing in this case. Right, so that's not surprising because they all need some sort of training data to work, and the data is just too small here. However, our methods, if you really do take the dialogue history into account and leveraging an existing and a backbone language model, you'll be able to do up to around 65%, which is 15%, 15 points better than just around 50. Right? And the other, on the larger data set, MathDial, so these other methods start working a little bit, but they're still by far not as good as LLM-KT, so our method. Right? And with the reason why we think it's easy to imagine what would be the intuition behind this method working better than other existing knowledge tracing methods is that existing knowledge tracing methods, they only consider the knowledge component labels and also whether the student answers the questions correctly. They do not really consider the whole textual context of this dialogue so far, and how did the student really interacted with the tutor before, right? And we think that all of that textual information is really the key to help make this model actually work on this data set. And also since we need we care about, providing feedback to teachers, we also want to make sure that these knowledge components are actually meaningful. Right? So one way to make sure that they're meaningful is to check them against the power law of practice, which is that just given more practice, do student knowledge generally tend to increase over time after more practices. And what we found is that for the most frequent knowledge components, there is some sort of an increasing trend. Although, we have to caution that since this data set is very small and the dialogues are very short, and there's also a large number of knowledge components, these results may not be the most reliable. And which is also what we found, that for knowledge components that occur less frequently, then the power law of practice is not really there. Right? And but generally speaking, this aspect really needs further examination. So what we've done in order to do that, what we've done is that we're now releasing our code. So because we understand that sharing this dialogue data can actually be troublesome. There are a lot of hurdles to go through, and you may not want to do that, but instead you can just take our code and try to evaluate it on your private data set, and we would welcome everybody to do that. Right, so that's kind of it. So this is the change to this layout a little bit, for the talk, but to just share about this recent paper that we submitted that I'm really excited about. And all of these papers, the codes and everything, they're open source online. You can feel free to take them and experiment on your data. If you have proprietary data, private data, you can't share publicly, but nevertheless, you use our paper to do some offline evaluation. Right, that's it. Yeah, so let's look at some questions.
That's brilliant. Thank you very much, Andrew. Yeah, that was really, really interesting. Are there any questions specifically on on either parts of the talk, but I guess. Oh, yeah, so putting the links in the chat, that would be handy.
For sure, yeah.
Yep. We can probably share the, would you be all right with us sharing the presentation slides as well?
Sure, yeah, I'll send you a copy of the slides. Let me also see if I can.
I'll send that around.
I can exit full screen and copy these in the chat. Okay.
Andrew, I had one question on the LLM-KT slide. It was a few slides back.
Oh, sure, yeah.
Where we needed to take that one there. Yeah. So that top equation there, we're just assuming independence of the mastery probabilities for that.
Yes, correct. Yeah.
So have you considered, or do you have any idea about whether kind of taking account of the structure of those knowledge components and the dependence of the knowledge components on one another would help or make a big difference, or is that not an area explored?
Yeah, for sure. That's a great point. And we didn't have time to do something like that. But yeah, I think that will help for sure. Yeah. So even in this part, right, we can probably use either this part, I don't know how we could do that. I mean, we could probably use the tree structure information. We could also just say we use a separate model where we just input, the combinations of all the knowledge components that are tagged here, and then ask the model to implicitly pick up the relationship between them, the interactions between them. So yeah, there would possibly be several different ways that we can deal with this. But yeah, I agree. Like that's for sure. The interplay among the mastery, the detailed content of these knowledge components should be very relevant and should help a lot.
Cool. That'll be interesting as well. There is a question there as well in the chat. Is there documentation or a log of the development process of DiVERT? So somebody's kind of interested in how it comes together.
Yeah, let me see. So for DiVERT, I mean, we all have the code available online soon, right? So yeah, but I'm not sure if that corresponds to the development process. I mean, it really probably, we'll probably just have to refer to the original paper. Yeah, we're gonna update the paper soon as well.
Okay. One more cheeky question, just to in that same line. So the question wasn't for me, but I'm kind of intrigued. When you and your lab start developing these models, do you go code first or mathematical model first? And do you go, when you're coding, do you start with notebook-based models, or do you dive straight in for kind of more structured Python coding?
Let me see. So it's hard to tell. I think that by far, I would probably be neither, I would say. So we basically just go data first.
Cool.
Yeah. So we basically just look at the data that's available. We kind of sort of have some intuition of what we want to kind of work on, what's the high level direction, but then what can actually get done. We look at the data and try to figure out, okay, what's feasible. And then we start with the mathematical framework before implementing everything. Yeah, so the implementation is the last step.
Cool. Yeah. I think that might help Summit as well. Cool. Brilliant. Thank you very much. I think that's all the questions there. So oh no, sorry, there is another another question. Summit, do you want to ask your question?
Yes, actually, I have, let's say, very weak foundations in math, but I would like to ask that as you at one of the last slides you found the
You're muted. Sorry.
Oh.
Summit, you've muted. I'm afraid.
Am I audible now?
You're,
Oh.
yep, we can
Oh,
hear
yeah,
you.
yeah.
Yep.
Okay. Okay. Actually, in one of the last slides, you showed how you formed a function for normalized probability of I don't yes, this one. So
Oh, this one, yeah,
what
yeah.
kind of
Mm.
background in mathematics do I need if I want to do these sorts of calculations?
Oh, let's see. That's yeah. I don't. I would say, yeah. I think this part is not really. You don't need to. You don't need much in terms of mathematical background, as long as you like in terms of actually implementing this thing. When you know how to retrieve, like I would say, as long as you know how to retrieve the output logits, that's all good.
Okay.
Like then you can basically it's just basically taking like two components in the output token logit vector. Then all you just gotta do is to look up the two components for the true false, and then normalize them, and that's it.
Okay. Thank you.
All right.
Brilliant. Oh, well, I've really enjoyed that. Thank you again, Andrew. I know Andrew has to rush off to give a lecture now after giving a little mini lecture to us. So thank you for making the time today, and I hope that's been valuable for everyone. And as I said, we'll share the video and the slides on the meetup group and on LinkedIn as well. Brilliant.